Good morning, ladies and gentlemen. My name is Liu Chan, a PhD student from Huazhong University of Science and Technology. It's a great pleasure for me to be able to attend this conference. Today, my topic is Modelica-Based modeling on low Earth orbit satellite constellation. The content of this presentation is divided into four parts. Firstly, I will introduce the background of our work. In recent years, as the demand for network communication has increased sharply, the idea of using low Earth orbit communication satellite constellation to provide the Internet from space has become popular again due to its low communication delay and full area coverage. A group of low Earth orbit communication satellite constellation projects represented by OneWeb, Starlink, Telesat, and Iridium Second have emerged in the world. Low Earth orbit satellite constellations have many advantages as follows. First, they have global coverage. Low Earth orbit satellite constellation can cover nearly full area on Earth, including remote areas. Second, they have low communication delay, around 20 to 50 milliseconds, related to orbit altitude. Third, they have high bandwidth, mainly based on Ka and Ku frequency bands, bringing higher communication speed. This figure shows schematic of a low Earth orbit communication satellite constellation. The existing simulation methods for satellite constellations can be mainly divided into the following three types. The first is to simulate the orbit, perturbation, structure, and ground coverage characteristics of the satellite constellation, based on software like SDK, and to support the constellation orbit and structure design. Second is based on software like OpenLate to simulate the communication process of paging, inter-satellite link establishment, link switching, delay, and other communication processes. To calculate the communication link performance and the multi-domain characteristic simulation of the satellite is the area where Modelica excels. So we want to propose a framework that can implement the above content in one simulation model. In order to realize the unified model of various simulation tasks of constellation, the constellation system model architecture is proposed as shown in left figure. Each color line with arrows in the figure represents a specific interface. The constellation orbit model calculates the number of orbital elements of each satellite in the constellation according to the given constellation design parameters. These orbital elements contain the position and speed information of the satellite and are transmitted to the ground station through the satellite-to-ground link. When user terminal 1 sends a request for establishing communication with terminal 2 to ground station, the communication request contains communication type and the latitude and longitude information of Terminal 1 and Terminal 2. Then, ground station can establish a communication link between the two places and calculate the link marking. The link interface contains communication frequency, transmission rate, connection status, communication date, and so on. The System Control Center generates the satellite orbit maneuver control signal and transmits it to the GNC subsystem of the satellite that needs to maneuver through the satellite to ground link. The GNC subsystem then generates the propel ignition command to the propulsion subsystem with the help of the flexible component interface definition method of Modelica language. The modeling of related components can be easily carried out. And here I will introduce the model realization of orbit model, satellite model, and system control center model. The orbit model includes the ideal orbit and the orbit perturbation calculation. The ideal orbit calculation is to convert the constellation parameters into the coordinates of each satellite at each time through the upper right formula. The orbit perturbation model applies the influencing factors in space to the satellite to bring it closer to the real situation. The main perturbations in space include non-spherical gravitational perturbation, atmospherical drag perturbation, lunisolar gravitational perturbation, solar radiation perturbation, post-Newtonian effects. The satellite model is composed of 4 subsystem models, namely GNC subsystem model, propulsion subsystem model, payload subsystem model, and power subsystem model. GNC subsystem consists of a satellite body model, a solar wind model, a sensor model, a flywheel model, and a controller model as shown in Figure A, which is mainly responsible for the altitude and orbit control of the satellite. Propulsion subsystem can be divided into a gas pressurization model, a propellant storage model, and a thruster unit model as shown in Figure B. Power subsystem includes 2 solar wind models, a battery model, a power controller model, and a load model. Payload subsystem is generally composed of antenna models and transponder models as shown in Figure D. The System Control Center model belongs to the ground segment. The main function in the satellite constellation is to maintain the stability of the constellation structure. The initial orbit factor is used to obtain the reference constellation configuration through this formula. And the subsequent actual orbit factor is calculated through a similar formula to obtain the actual configuration of the constellation. When the deviation between the two exceeds or is about to exceed the set threshold, an orbital maneuver is required. Orbital maneuver speed pulse is calculated through the following formula. And here is an example system model of low Earth orbit satellite constellation, which is established in the multi-domain simulation environment MWorks. MWorks provides management of models and integrative solvers, which supports Modelica Standard Library version 3.2. In the third part of this presentation, I will showcase some simulation results. This table contains some simulation parameters. The constellation orbit parameters in this table are from Iridium Next constellation, and the following will analyze the system simulation results from three aspects: orbit coverage, communication link, and satellite status. Orbit coverage simulation mainly focuses on satellite position change, constellation structural maintenance, and ground coverage. The position change of satellites is shown by the longitude and latitude of sub-satellite points, as shown in Figure A. The longitude of the sub-satellite point of satellite 121 and satellite 122 is between 180 degrees west and 180 east, and the latitude of the sub-satellite point is between 85 degrees south to 85 degrees north. Figure B and C show that under the action of the speed pulse signal generated by the System Control Center, orbit deviation can be controlled within a range of -2 degrees to 2 degrees. Figure D shows that during the normal operation of the constellation, the two places have always been covered by satellites, and the maximum number can reach 5 satellites. The focus of communication link simulation is to evaluate the communication quality of the two places and the impact of inner satellite link switching on the communication quality. Figure A and B shows the linker attenuation of the upper satellite to ground link. The lower satellite to ground link are in the range of 120 to 145, and the inter-satellite link attenuation is in the range of 194 to 204. Figure C shows the overall communication margin of the full link is in the range of 15 to 50. Figure D shows the process of inner satellite link switching. During the operation of the satellite constellation, the energy balance characteristics of three satellites in constellation are shown in Figure A and B. It can be seen that the state of charge of the three satellites remains above 80%, and the output power of the solar array during the period with sunshine, which is 3,000 watts, indicating that the satellite's energy system can satisfy the energy consumption under working conditions. Figure C shows that the result of satellite altitude adjustment, the altitude angle is controlled within 1 degree. Last of all, the content of this paper has been summarized as follows. Firstly, the established system model can unify constellation orbit simulation, communication link performance simulation, and the satellite status simulation. Secondly, The currently established system model is more like a framework, and the content needs to be continuously filled in. Thirdly, the simulation application examples show that the constellation system model not only supports the characteristics and analysis of key components, but also supports the overall performance evaluation of the system. That's all. Thanks for listening.